Welcome to your lesson regarding Chapter 4, Aqueous Solutions and Solution Stoichiometry. Today's first lesson has the topic of general properties of aqueous solutions. We have our note pack open to page 1 from our Chapter 4. And in this section we are highlighting some vocabulary in terms of electrolytic properties for solutions. We begin by taking a quick peek of some review terms. The word solution. We know that those are two or more ingredients that have been physically blended. The term solution is another name for a homogeneous mixture. When we take a solute and dissolve it into a solvent, we create a solution. For example, if we were to take sodium chloride and sprinkle it into water, salt water, salt would be the solute, water is the solvent. We see that every one of our solutions in this particular chapter are going to be dissolved in water. So water solutions. Alrighty. If something does dissolve in water, it's said to be soluble. A solid dissolving in water is soluble. If it does not dissolve in water, it is insoluble. And the term miscible is that word that would represent two liquids that dissolve into each other. Immiscible are two liquids that would not dissolve into each other. Since our entire chapter is devoted to water, it's important to understand those physical and chemical properties of water that make it such a universal solvent. When solutions are created, we have a solute dissolving in water. The little AQ sign represents that it is indeed an aqueous solution. Water is such a good solvent because it is polar, and it's important to review the term polarity. We introduced the term in first-year chemistry but did not spend a great deal of time. We said a polar molecule is one in which regions of positive and negative both exist within the same structure. A bar magnet is a good example of a polar substance. An ordinary bar magnet has a region that has a positive charge and a region that has a negative charge. It is said to be a dipole or have moments of polarity. A water molecule has the same structure. That's supposed to be an H. Here's an H, and this is an oxygen. Two H's and an O bonded together. If I think about the Lewis dot structure, the electron configuration of a water molecule, this oxygen has two electron sets these are two sets of electrons that are indeed exposing an area that is very electronegative. This region on the oxygen is partially negative. The region on the hydrogen is left partially positive. What I'm drawing is a little Greek symbol, a little squiggly S, that represents visually the term partial. It is partially positive and partially negative. The oxygen is very electronegative. It is pulling the electrons in the shared pair towards its center. So the electron-rich density of oxygen makes this region quite negative, and those hydrogens are left with a positive charge. The bond angle of a water molecule, and again we're looking at some molecular geometry, is approximately 105, and it's really not degrees Celsius. The bond angle is just 105 degrees. So the region between the two H's, water is a bent geometry. Water is not linear where the H's come straight out, but it is bent. So these areas that are positive and an area that is negative make a great region to attract other particles that have positive and negative regions on them as well. We're going to be asked to draw a water molecule, and really it can be as easy as what I've done. Take a hydrogen, connect it to an oxygen, connect it to the second hydrogen, and show the two dots of electrons that are unpaired. Two sets of unpaired electrons make this region partially negative and this region partially positive. With a bond angle of approximately 105 degrees between the two H's. Water is a polar molecule. Because of these areas that are charges with partial negative and partial positive, we start to see areas existing. For example, if I have a sodium ion or a chloride ion, ions are built of these charges, we could see an attraction between these oppositely charged regions of ionic compounds in a polar molecule. This process known as solvation, creating a solution. That's a nice little pop up there, sorry. Creating a solution through a process known as solvation. If water, and it is in our chapter, serves as the solvent, the process has a more specific vocabulary term known as hydration, when water is the solvent. And the process of breaking ions from the ionic compounds known as salts, when they fall apart, we call that dissociation. So the process of hydration is really just breaking apart ions of commonly called salts. Salts is just another name for any ionic compound. Ions that have charges and attract the opposite charges on the water molecules. Let's show a sample of a salt crystal being hydrated through the process of solvation. This is what I'm going to ask that we draw together in the bottom of page 1 of our note pack. This is a repeating pattern of sodium chloride crystal. Think about the negative opposite charge next to positive, next to negative, next to positive. See this repeating pattern of a sodium chloride. In this particular picture, the positive ion is representing that of a sodium ion, and the chloride ion is represented here with the lighter green. So we see a repetition of Na+, Cl negative, Na+, Cl negative. When they are organized into a crystalline structure, they are in the solid phase. If I think about sprinkling a solid crystal of salt, very highly organized with a repeating pattern, the water molecules begin to bump against it. The water molecules, which are shown here, HOH, notice the molecular geometry being bent. The region that's up here is negative on the oxygen, partial positive here on the hydrogens. Notice how it can form almost like a little pocket, a pocket of an area to pull in the oppositely charged ion. If water molecule areas here that are positive, sorry for that pop-up, still coming up here to be positively charged, well, it's going to be attracted to the negative chloride. And we start to see the hydrogens from water all surround the negative ion. Take a peek here. The oxygen, which we know has a polarity of negative charge, it's a negatively charged region. So again, it's going to attract the positive ion of sodium. Knowing the basic laws of electricity and opposites attract, this process is pulling apart the ions and surrounding them completely with water molecules. You can see from the process that the negative chloride, look at those H's all surrounding it. Oppositely charged particles. Here's the sodium ion with a positive charge, completely surrounded by the negative oxygen from the water. Pause your video and take a moment to draw, just as I have on the slide here, the solid phase of sodium chloride, very highly organized. Then the solvated ions. Those solvated ions surrounding the water molecules. When you have this drawn on the bottom of page 1, start the video up again, and you'll flip to page 2 of your notes. Let's check in our own heads some concepts for understanding. How does water dissociate ionic compounds? Water dissociates ionic compounds through the opposite charges, just a basic law of electricity. Here we have a repeating pattern of positive and negative ions in a solid phase. A water molecule A water molecule is going to surround the positive region by using its oxygen. The water molecule will surround the negative ion by using its hydrogens with the opposite charges associating. Water is a polar molecule. What does that term mean? Check for understanding. A polar molecule? You got it. It's a molecule that has a region that is a little bit positive and a region that's a little bit negative, all within the same structure. Water is polar because it has areas that are positive, those are the hydrogen atoms, and an area that's negative, the surrounded electrons on the oxygen. Water is polar because it has an uneven distribution of charge, an area that's positive and an area that's negative. What's the difference between ionic and molecular compounds? Oh, a very strong background because we need to dissociate ionic, leave together the molecular. Perhaps you remember from year 1, ionic compounds, when we take a metal, who's a positive charge, and hook it to a non-metal, which has a negative charge. Positives and negatives, we crisscross charges and write formulas. Ionic compounds are made of ionic bonds. They're made of charges. Molecular compounds, on the other hand, are when all nonmetals group together by something called a covalent bond. There are no such things as charges in molecular compounds. Ionic compounds, they're built of charges. These are commonly called salts. Molecular compounds are made of nonmetals all grouped together by covalent bonds. They are non-electrolytes. Top of page 2, the term solubility. It is defined as how much of a substance will dissolve in a given amount of water. It's typically given a unit of grams of solute per 100 mils of solution. How much can we get to dissolve in water? And such a large variety of salts, the solubility varies enormously from salt to salt. If they do not dissociate, we call those an insoluble salt. However, most solid compounds, ionic compounds, do indeed dissolve and dissociate. Those ions are separated and therefore can move around. The ionic compound is said to dissociate and form its component ions. We practiced some of those in the opening day of our notes. Water can dissolve any non-ionic compound if they have polar bonds, so likes dissolve likes. We can get ordinary table sugar, C12, H22, O11. It will dissolve in water because it is polar, but it does not dissociate and form an electrical current. So solubility, does it dissolve in water, and if so, how much? Ionic compounds dissociate. Molecular compounds do not dissociate. Remember, just kind of write some side notes with me here. We have ionic compounds that we have mentioned in our first year chemistry as being those compounds that are made of a metal hooked to a nonmetal. We talked about a positive ion hooking to a negative ion. We crisscross charges to come up with an electrically neutral compound. Ionic compounds are commonly called salts. Water-soluble salts are strong electrolytes. And you'll see that if indeed a salt dissolves in water, it will 100% dissociate, forming lots of charged particles, and the light bulb will glow brightly. The other category of compound are called molecular compounds. And molecular compounds, when we take nonmetals and hook them to nonmetals in the same structure by covalent bonds, nonmetals plus nonmetals, 2, 3 different elements hooked together to create a molecular compound, There is no such thing as charges. There are no ions. These tend to be non-electrolytes. So strong electrolytes versus non-electrolytes can be quickly categorized simply by denoting if it's an ionic or molecular compound. But what about that in-between category? Those types of compounds that build what we called weak electrolytes. Weak electrolytes come from molecular compounds in a very special category of molecular compounds known as weak acids. One of the last units we studied in first year chemistry was acid-base chemistry. Just a very quick definition from the Arrhenius definition, we know that acids ionize to give hydrogen ions. Acids start with an H. Any hydrogen hooked to some negative ion is a formula representing an acid. HCl, hydrochloric acid. H2SO4, sulfuric acid, and so forth. So these compounds, known as acids, now several of these acids will 100% dissociate. These will be strong electrolytes, but the vast majority, by far the majority of acids are known as weak electrolytes and only partially dissociate. So thinking this through, molecular compounds in water usually consist of intact molecules dispersed throughout that solution. Consequently, most molecular compounds are non-electrolytes. This is the term that will fill in your blank, non-electrolytes. There are, however, a few molecular substances whose aqueous solutions do indeed contain ions, and the most important of these are known as acids. Now let's proceed further with that discussion on acids. We know acids form hydrogen ions, H+. Sometimes we've called those hydrogen ions protons in the Bronsted-Lowry acid-base theory. Hydrogen ions, when released, make the solution acidic, and that's indeed what we measure on our pH scale, is the concentration of those hydrogen ions in the water. When strong acids are placed into water, strong acids indeed mean 100% dissociate. And when they do dissociate 100%, they will release their ions. Weak acids do not dissociate completely. They only partially ionize. There are 7 strong acids that we need to memorize. And I hardly say that, but this really will be so helpful to you. Because see, if we memorize the 7 strong acids, you now know all of the weak acids as well. Memorize the 7 strong electrolytic acids, and here they are. I'll write their formulas. You write them along with their names. The binary acid hydrochloric is strong. Hydrochloric acid. It will 100% dissociate when placed into water. So what the word strong means, when HCl, which is actually in a gaseous form, is placed into water to create a solution, see, the acid forms after it's placed into water, 100% are going to be lying to the right of this arrow, forming products. And of course, these would have adjectives AQ, aqueous ions. Gaseous hydrogen chloride, when placed into water, forms an acid, hydrogen ions and chloride ions, 100% dissociation. So let's keep writing our 7 strong acids. We have HCl, another binary acid, HBr, hydrobromic acid. The third binary acid is HI, hydroiodic acid. Hydroiodic acid, HI, will 100% dissociate. We have HClO3. This is a ternary acid from the polyatomic ion chlorate. H turns to ic, and we get chloric acid. Hydrochloric, HCl, and plain old chloric, HClO3. And there's another strong acid that contains chlorine. It comes from the polyatomic ion perchlorate. So this is perchloric acid. The sixth acid that's considered strong is nitric acid. And the last one is a diprotic acid, sulfuric. From the polyatomic sulfate, we have sulfuric acid. HCl, hydrochloric. HBr, hydrobromic. HI, hydroiodic. HClO3 is chloric. HClO4, perchloric. HNO3, nitric acid, and the last one, H2SO4, sulfuric acid. 7 strong acids. Now, I need you to memorize those because now you know all of the weak ones as well. If you're looking at a formula for a weak acid and it's not one of these 7, it will only slightly turn that light bulb on, giving a partial ionization and a very dim glow on the bulb. 7 strong acids, and now we know the weak ones. Let's further this with just a little bit of an example on the top of page 3 to just clarify further what strong versus weak means. I'm going to just add a new little slide in here. To write the dissociation for hydrochloric acid, hydrochloric 100% dissociates, we're going to have all of the product lie to the right of our arrow. 100% pushes right to H plus and Cl negative. This represents a strong acid. Compare that to acetic acid, and this one was shown in our little video a moment ago where it slightly turned on the bulb, just a dim glow of that light bulb. Truth be known is only about 1% of the molecular form of your acid is able to separate into the ions. That's not very many, is it? That about 99% lies in the molecular form, and here you have the ionic form. So you can see an electrolyte is truly defined as the more and more and more ions that are floating in the water, the brighter the bulb is going to glow. A very weak acid, such as vinegar, and this is what acetic acid is vinegar. If I place that into water, very few ions are going to form. So if they're mostly in the molecular form, we're going to have a very slight glow, a weak electrolyte. Give it some thought with me. What are the dissolved species in the following solutions? And this is really going to help us in the nomenclature part. So I'm glad that your summer assignment had you practice nomenclature. If we give it some thought, what are the species that lie in KCN? First of all, let's begin. Is it ionic or molecular? Well, I notice it's a metal to a polyatomic group of nonmetals. Potassium is that ion K plus 1. CN, carrying a negative 1, is called cyanide, right off of our polyatomic ion chart. Potassium cyanide, as a solid, will indeed dissolve into water. It is water soluble, and 100% of salts will dissociate into their ions, the aqueous ion of potassium and the aqueous ion of cyanide. Now friends, remember, ions only exist in water solutions. Without the water, potassium cyanide is a white solid salt. When dissolved into water, it indeed dissolves and 100% separates into their ions. So what are the species present? Well, the species are potassium ions and cyanide ions. How about NaClO4? NaClO4. And again, this starts as a solid. I notice it's ionic, a metal hooked to a polyatomic ion group of nonmetals. Sodium carries a +1 charge. The polyatomic ion ClO4 negative is called perchlorate. As a solid, this would not conduct electricity. There's nothing to move the ions around. But when I place it into water, those ions 100% separate, giving me the positive ion of sodium in the aqueous solution and the negative ion perchlorate in the aqueous form. Sodium ions and perchlorate ions separate, and we would see a light bulb turn on when dissolved in water. Without the water, no electricity flows, but in the water, these ions separate and complete circuits. What would the dissociation equation for ammonium phosphate look like? Our compound of ammonium phosphate. Do you have your periodic table and polyatomic handy? Ammonium is the polyatomic ion NH4 carrying that +1 charge. Now phosphate is a polyatomic ion as well, PO4. It carries a -3 charge. So remember how we take a group of polyatomic ions by placing it inside a parenthesis to create an electrically neutral compound. The ionic compound called ammonium phosphate is indeed water soluble. Without the water, it's a white crystalline salt. Placed in the water, it will 100% separate and let go of its ions. Out come the positive ions and a negative ion. How many ammoniums? See how there's 3 of them in there? There's 3 groups of ammoniums, NH4 plus, aqueous ion, and 1 group of the polyatomic ion called phosphate, aqueous. Now friends, I cannot stress enough, most people, if they lose points or quiz questions or whatever might get marked wrong, it's because of this little tiny detail. Ions carry charges. Please write that in your note pack with me. Underline it a couple times and let me stress what I'm saying. Without the positive sign on ammonium or the -3 sign on the phosphate, I cannot give credit because electrolytes must be charged in order to conduct a current. Charges flowing through water are electrolytes. If you look back up here and you do not have a +1 on your sodium or a -1 on your perchlorate, put it there or you're going to be so mad that you get it marked wrong without those charges. Same up here. Ions carry charges. They must be there in order to earn your credit. Which solute will cause a light bulb to glow more brightly? We have some choices here. We have CH3OH versus MgBr2. Notice this is a molecular compound. It's all nonmetals grouped together. Molecular compounds, although they will dissolve in water because it is indeed polar, it is not built of ions. It will dissolve, but it is a non-electrolyte. No ions in there at all. Magnesium bromide we recognize as an ionic compound, metal to nonmetal. When magnesium bromide gets placed into water, it will be a very strong electrolyte, simply because I'm going to make a magnesium ion and we're going to let go of 2 bromide ions. Notice how I'm putting the charges there. There's 3 ions formed from every little crystalline solid here. Lots to turn on the bulb and let it glow brightly. Methanol, no glow, and then magnesium bromide indeed will glow brightly. We have a little drawing exercise as part of this final lesson on electrolytes. Let's take a peek. I'm going to give myself a little more room here. For instance, we want to draw a diagram that represents aqueous solutions of each of the following ionic compounds. Make each drawing contain 6 cations and then the appropriate number of anions. Make the charge of the ion relative to its size. So let's model what this is saying. The only parameter is we have to have 6 positive ions and then the appropriate number of matching negative ions. First one in the box says it's nickel, Roman numeral 2, sulfate. So let's turn that into a formula. Nickel, Roman numeral 2, tells me it's a +2. Sulfate, polyatomic ion, carries a -2. So we have 1 unit of a +2 electrically balanced with 1 unit of a -2, NiSO4. So if I have 1 nickel, I need 1 sulfate. If I have 6 nickels, I'll need 6 sulfates. And notice that the magnitude of the charge indeed is the same. Both are carrying the same charge. They're going to be the same size model. I'll use green to represent the nickel. And I'll just put that as a +2, 2, 3, I'm just randomly placing them, 4, 5, 6. 6 units of a +2. I'll use blue to represent the negative ions, and they're just going to be separated. So I'll place one here, 1, 2, 3, likes would repel, so 4, 5, 6. This represents a random dispersion of the separated nickel ions from the sulfate ions. Let's try another. How about calcium nitrate? Calcium with its +2, nitrate is a -1. So when I write my formula, I need twice the number of negative ions, 2 units of the negative nitrate, to electrically balance the calcium. So I'll use red this time. Now calcium is a +2, so I want to make it twice as large as the -1. So I have to draw 6 positives. So 1, 2, 3, 4, these are all the same size, 5, 6. If I have 1 positive, I need twice the value of negatives. So keep in mind here, 2, 4, 6, 8, 10, 12. We have a +12. We're going to need a total of -12 to give us 0. It means we're going to need 12 little circles of -1s. I'll make them half as big. Half the size, but represents half the magnitude of the charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Calcium nitrate. Keep in mind, what we've done is saying for every 1 calcium, we had 2 nitrates, and that ratio would come out to be the perfect 1:2. How about sodium phosphate? Sodium phosphate. Well, let's go to work writing that formula. Sodium is a positive ion, carries a +1 charge. Phosphate is the polyatomic, carries a -3 charge. So when we crisscross, we get Na3PO4. Now keep in mind we're told to draw 6 positive ions. So I'll use blue this time, and they're going to be a +1 charge. So I'm going to do 1 sodium, +1, 2, 3, 4, 5, 6, randomly placed Alrighty. Now, how many negative ions will we need to draw? I'll put those in green. Well, you can see it only takes 1 to electrically balance 3 units of sodium. It's got to be pretty big too, because it's a -3 Na3PO4. Na3PO4, and that is sodium phosphate. So see how the same number of positives are balancing the total number of negative charges, Na3PO4. We have one more to draw together to finish off our lesson on electrolytes. Aluminum sulfate. Aluminum sulfate, well, aluminum with its +3 charge, sulfate, which carries its -2, so we have Al2, parenthesis, SO4, taken 3 times. So, let's use blue to represent the +3 aluminums. We have to draw 6, so there's 1, 2, 3, 4, 5, 6. Alrighty, so that's the largest circle with its +3 charge. Now, how many sulfates will we need? Remember, for every 2 aluminums, we have to draw 3 sulfates. Let's do that in red. So here's 2 aluminums. I have to draw 3 sulfates. And they're going to be -2, so I'll make them just a little bit smaller. Al2, SO4, taken 3 times. So I've got to draw 3 more here. Alrighty. And then 3 more here. And just random. That's all there is to that. If we had placed a 6, a 2-to-3 ratio, 3, 4, 5, 6, 7, 8, 9, there's a 9. 2:3 is 6:9. So all we've done is just represented by the size and the magnitude of the charge, and making sure that we have the same proportion that represents our subscripts.